We age 1 year between every birthday. As humans, we experience time at a steady, reliable pace of exactly 1 second per second. Because this rhythm is so constant in our daily lives, it is easy to assume time acts as a rigid, universal background metronome, ticking away at the exact same pace for every object in existence. But that assumption is incorrect. Time is flexible. In fact, every time a space telescope points out into the void, it looks backward in time. Light from faraway galaxies takes millions of years to cross the vast distance of space. When that light finally reaches our lenses, we see those star clusters as they existed in the distant past. Time is physically malleable. If we fail to account for that physical flexibility in our atmosphere, modern terrestrial technology completely breaks down. Over a century ago, Albert Einstein established the theory of relativity. His core premise stated that space and time are physically linked together. Spacetime functions as a material that bends and stretches depending on the physical forces acting upon it. The flow of time for any object is dictated by two variables: how fast it is moving and the strength of the gravity pulling on it. To accurately predict how anything travels through time, whether it's a starship or a smartphone, we have to isolate and measure exactly how both of these physical variables distort the clock. The universe has a strict speed limit. Nothing can travel faster than the speed of light, which calculates out to 186,000 miles per second. This animation demonstrates the inverse rule of variable A. As a physical object accelerates through space, it experiences the passage of time slower. Scientists proved this rule by executing an experiment utilizing two highly precise synchronized atomic clocks. They left one clock entirely stationary on the ground and placed the second clock on an airplane, flying it rapidly around the globe in the direction of Earth's rotation. When the experiment ended, scientists compared the readings and found the fast-moving airplane clock was slightly behind the clock that stayed firmly on the ground. Achieving high physical velocity reduces the rate at which an object experiences time compared to its stationary surroundings. Now we look at variable B. Einstein's theory dictates that mass physically curves both space and time. Look at this cross-section of Earth's gravity well. Heavy gravity at the surface compresses spacetime, slowing the clock. As we pan up in altitude away from Earth's mass, gravity grows weaker. In this thinner gravity, time speeds up. The global positioning system, the network of GPS satellites orbiting Earth, is subjected to both variable A and variable B simultaneously. Let's calculate the speed variable. GPS satellites orbit at a rapid 8,700 miles per hour. That extreme velocity slows their internal clocks down. Next, we calculate the gravity variable. Orbiting 12,550 miles above the Earth, in extremely weak gravity, their internal clocks speed up. This orbital environment creates a complex relativistic math problem, creating a physical tug-of-war over the satellite's internal perception of time. When we pit orbital velocity against weak gravity, one of these forces has to win out. This scale weighs the two competing forces. The accelerating effect of weak gravity in orbit overpowers the slowing effect of the satellite's sheer speed. The combined calculation reveals the GPS satellite experiences time fractionally faster than 1 second per second. Bound by unbroken physical law, the satellite travels forward through time faster than the humans relying on it down below. This tiny time differential dictates the accuracy of our global navigation networks. To keep the system running, scientists constantly apply relativistic math to correct the satellite clocks, forcing them back into sync with Earth time. If the time travel correction stopped, satellites would instantly miscalculate their spatial positioning relative to ground receivers. Without the correction, those errors would compound fast. Global GPS maps would become physically inaccurate by several miles within a single day. Time travel is an active, daily mechanical reality that engineers must delicately harness to keep modern society functioning.